Hello everyone, welcome to this video. In this video we are going to discuss about how process creation works in the Linux operating system using the C programming language, and also what kind of interfaces the operating system provides the user to create processes. So as we all probably know, like in Linux, processes are one of the most integral part of the entire system. No matter what you want to do in Linux, be it executing a simple hello world program in C, a process needs to be created, right? So almost everything in Linux involves process creation and process destruction. So in any intro to operating system 101 course, it's usually said that one of the basic ways to create processes in Linux is using the fork library call or the fork system call. Oftentimes, fork is referred to as both a system call and library call. The fork library call is one of the ways to create processes in the Linux operating system. We'll start by taking a look at how we can use the fork library call, which is provided by the glibc library, how we can use that fork call to create a process in C. So yeah, let's get started. I'll create a simple program which will create a child process, and the child process will print something. That's it. Let's see. So I've already created a file pfork.c. So I'll start by including some header files. These are the header files we'll be needing. After this, we will create a tiny function declaration. So this is going to be the function that our child process will be executing. Let's define this function. We don't want to do much inside. All we want to do is we'll say this is child. Let's say child in small. This is child process with PID and the PID. And we will use the getPID library call to get the PID of the current running process. And that's it. That's all the child is going to do. Next, we will write our main method. This will store our child PID. When we are working with processes and we want to store the PID of a process, it's always suggested to use the provided type diff, which is PIDT. And we will also have a variable for storing the child status when the child exits. Now we will just add a log statement which says parent, the this is the main program PID. So this will be the PID of the main parent process or the main program. And now we will invoke our fork call. So what happens now is, after this call, everything that happens after this line number 21, where the fork call has been invoked, whatever comes after this will be happening both in the child process as well as in parent process. When the parent process scheduled, the lines after this will be running in the parent process, or when the child process is scheduled by the kernel, whatever happens after this will be running in the child process. But what I'm trying to say is that everything that comes after this point will be cloned between both the parent and the child, right? Now, how will we know that we are in the parent process or we are in the child process? We will know that using the return value of the fork. The fork call, it returns 0 in the child process, and in the parent process the return value of fork is the PID of the child process, and that's how we can differentiate, like whether the code is running in the parent process or in the child process, right? So we will use the child PID. So if child PID not equal to 0, it means we are in the parent process, and once again we will log that. So this is parent, this is parent process with PID get PID. So if all goes well, this PID and this PID over here, so the PID we are printing in line number 23 and the PID we are printing in line number 18 should be same, because like the main program is the parent process, right? And we will also try to log what we get back from the fork call. So parent, this is fork return value. Actually, rather than checking with not equal to 0, we can do something like greater than 0, because fork can return -1 as well. -1 usually signifies the child creation fails, that is fork somehow faced some error and child process could not be created. So when it's greater than 0, it means the child got created successfully and we have the PID of the child. Else, if child PID equal to 0, which means we are inside the child, and if we are inside the child, we will call our child proc function, and that's it. We don't want the child to do anything else, hence we will simply say exit 0, or else if we don't do exit 0 here, after child proc function is executed, it will also try to execute whatever comes after this line, which we don't want. We want the child process just to execute this child proc function, and we want to get done with it. Post that, we want to wait for the child. We want the parent process to wait for the child process so that it can extract the status of the child process when the child process exits. If we don't do this, there is a possibility of creating zombie processes which will stay in the system. We don't want that. However, we won't go into zombie processes and the significance of wait in this video. But what we need to know here is whenever the parent creates some process, it's the parent's responsibility to wait for the child and extract the status, or else we are at the we might end up creating zombies. And finally, we can simply log the exit status code of the child. Okay, that's it. So that's a simple program that creates a child process, waits for the child process, lets the child process execute a function, and we log all the PIDs everywhere and we exit our program. So let's try to run it now. Okay, so we have got pfork.c. Let's compile it, -g, so that we have the debug symbols. Pfork.c -o pfork, and our code is compiled. Let's run it. So let's see what happens. PID of our main program, or the program that we are executing, is 18261, which comes from this line. After that, so after this line, the for call happens, and the first output in this case we are getting is from the parent, which is this is the parent process with PID 18261, and as I mentioned earlier, since this code ran as expected, these two PIDs are same because our parent process and our main program are one and the same program. Then it prints what it got back from fork, and that is 18261, which I believe is wrong because yes, so by mistake I used get PID here as well. Let's change it to child PID, and let's execute our code once again. Yeah, so this time our main program PID is 18308, the parent process PID is 18308, and the return value from fork is 18309. So this is the child. This is the child that got created, and the PID of the child is 18309. After this, we we get to see what's happening inside the child. So this is coming from the scheduled child process that the kernel has scheduled for us. This process and this process is completely different, as we can see that the PIDs are different, and here the child process is doing only one thing, that is it is printing its own PID using the get PID call, and as we can see that's 18309, and again this value and this value is same. This is because the child is calling its own, is printing its own PID within from itself, and that has to be same with the return value of the fork that the parent got, and hence these two values are same, right? Finally, the parent extracts the status of the child using the wait library call, and the status is a successful exit, and hence we get a status of 0, right? That is our simple process creation code over here. Now coming back to process creation and this code, process creation is something which user cannot do on its own, or a user space library cannot do on its own. The library call which we used in this case is fork. It is a user space library call. By user space, what I mean is it's not in the kernel space, rather it's in the user space that this library call is being executed, and user space call doesn't have the privilege or the capability to actually go ahead and create a process, which means this fork call at the end of the day is nothing but a wrapper over some system call which is provided by the kernel. Again, what are system calls? System calls are interfaces provided by the kernel which can be used by user space program to take advantage of the features provided by the kernel. So let's say we want to open a file, the user space code needs to invoke a system call such that the kernel knows that the user wants to open a file, and the kernel will take over and it will open the file on behalf of the user, and that's how the end user is able to open a file. So what I'm trying to get at by saying all this is there has to be a system call involved which created the process on behalf of the fork library call. Usually the system call that's responsible for creating processes is sysfork, like sys underscore fork, which is provided by the kernel. And it said that the fork library call is a wrapper on top of that. But let's see what actually happens under the library call, under the fork library call, and which is the system call we end up, the library ends up calling. One very handy way, if you want to check what are the system calls what are these kernel system calls your program is invoking, is the command called strace. So strace is a Linux utility command which lets you trace the system calls and signals. So what we will do is we will do strace -f. -f is a flag which allows strace to attach itself to child processes as well. In this case, we are forking a child process and we want strace to attach itself to the child process as well. The command is strace -f p fork. So now each line is actually a syscall that the kernel is making to in order to execute this program. So usually it starts with number of things like the bash invoking the execv call to execute the pfork program, a bunch of mmaps to load the program into memory, and lots of things, but we can ignore these. And what we are interested in starts from somewhere around here. We call the write system call to print this line. This is the main program, as you can see, and in this time the PID of the main program is 18406, right? Then immediately after that comes our fork call. And interestingly, there is no sysfork which is being called over here, but the kernel is calling something called clone, or rather the fork library call is calling something called the clone system call, which is interesting. Like, so there is no there is no sys underscore fork, rather there is a system call called clone that is being used under the hood by the fork library call to create the new process. So if you see here with clone, we are passing these three flags, and the output of this clone call is the process 18407. This is the PID of the child process to which Strace attached itself. And the next thing goes on quite as expected. Like, then once again we call the write system call. This is the parent process. Then we go to the next line, which is the this is return this is fork return value, which is here, which is somewhere here. Then it shows what happens in the child process. So unfinished means this process is still running. And then, yeah, so this is the child process with PID 18407, and we can see that it was executed from within the child. One nice thing that stress does for us is we know which statement is being executed from which process, right? So it always shows the PID, and that's the utility you get if you use the -f flag with stress. It also shows when a process is incomplete and when a process is when a process is finished and or when it's unfinished. So in this case, this is the child process. Whatever it was getting printed, but it was not finished, so it marks it as unfinished, and then it says that write resumed, right? And finally, we come at the wait system call again, which happens from the parent. The child exits, which is over here, I believe, like line number 27. The child exits, and after that, in the final line of the code, we print child exited with code 0, right? And that's the output for stress. So the most interesting part in this whole log is fork. Although we do supposed to have a system called sys underscore fork, still the glibc library, I believe the library that I am on right now is let's see. So I am on the 2.34 version of glibc, which is quite a modern version of GNU library. And the GNU glibc, instead of using sysfork, is using the clone system call to create a new child process. Okay, so now that we know that the real magic is done by the clone system call, which is called by the GNU glibc fork library call, let's see what is the clone system call. And for that, the perhaps the best place to read about it is is the manual provided by Linux. So if we do man2 clone, we get the manual of the clone syscall as well as the clone library call. Okay, so let me zoom a bit more. Yeah, if we check out this manual of clone system call, you will see that the first disclaimer that is provided in the description is that these system calls create a new child process in a manner similar to fork, right? Clone system call also creates processes. The fork system call, which also goes by the name sysfork, it also creates child process. Then why suddenly the glibc fork implementation let go of the sysfork system call and they adopted the clone system call? The reason is, if we go through this manual, the reason is the clone system call or the clone 2 system call, which is the one that glibc uses, is way more powerful than what the fork system call alone is able to do. So what the fork system call essentially does, it creates a fresh child and it allocates. So by definition, in Linux, a child process gets its own copy of the PID descriptor table, its own copy of virtual memory. A child process created by the fork system call it's completely separate from the parent process. Like, it shares nothing with the parent process. In modern implementation, perhaps it shares the memory with the parent process initially, but then we have the concept of copy on write, wherein whenever the child or the parent makes the first write on the memory, the memory is separated, like the memory is unshared. So what I'm trying to say here is, like with fork system call, GNU C library doesn't have much control over the characteristics or behavior of the child that's being created. That is, with fork call, the child gets its own separate resources in every aspect. Like it shares nothing with the parent. There are instances, like there are widely used instances in the kernel and in the operating system, wherein the user space glibc library needs finer control over what resources are shared with the child and what resources are not shared with the child. Unlike fork, the clone system call gives this freedom or gives this advantage to user space programs to decide what are the resources that the child should share with the parent and what are the resources the child should not share with the parent. Clone accepts a number of flags, and this manual lists all those flags. If you see, if we have the clone files flag set, then calling process and the child process share the same file descriptor table. And if it is not set, the child process inherits a copy of all the file descriptors opened in the calling process at the time of the clone call. Subsequent operations that open or close file descriptors or change the file descriptor flags performed by either of calling process or the child process do not affect the other process. So it gets a completely different instance of the PID descriptor table if clone files flag is not set. However, if it is set, both the parent and the child share the same file descriptor table. Similarly, if we go to the flag called clone VM, if we set this flag called clone VM, or if we pass this flag clone VM while calling the clone system call, the parent process and the child process will share the same virtual memory. The child will not get its own separate virtual memory. Now, why are these things required? Like, why do we want such precision control? Well, there are multiple instances. One of the major instances, or one of the major reason why we need such sharing of resources between parent and child, is for the creation of NPTL threads or P threads. So NPTL is basically the native POSIX thread library. It's Linux's implementation of POSIX threads. So from a kernel point of view, there is no concept of threads, right? There is nothing called threads. Every thread gets the task structure or the task struct just like a process. What differentiates a thread from a process, it's how the thread behaves and what resources the thread shares with the parent, and that is controlled by user space. So the concept of thread versus process, or the difference of thread versus process, is something which is defined in the user space, right? And it's up to the user space to decide what things to share between the process and the child to qualify a process to be termed as a thread. That is one of the places where the clone system call is heavily used. So when we are creating a pthread, what the glibc library will do is it will pass the flags clone vm, clone fs, clone files, as well as the signal handler table clone sighand to the clone system call, so that these resources are shared between the parent and the child. That is the power of clone. That is the flexibility that the clone system call brings to the table, and that is something which the traditional fork system call didn't provide. Now if we see the documentation or the manual of fork, we will see that, well, this manual is way shorter than that of clone because of the obvious reasons. And we will see this disclaimer here that since version 2.3.3, rather than invoking kernel's fork system call, the glibc fork wrapper that is provided as part of the nptel thread implementation invokes the clone system call with flags that provide the same effect as the traditional system call, right? So a call to fork is basically equivalent to a call to clone to specifying flags as just as sigchild. What does the flag sigchild do when you are using clone system call? It simply sends a sigchild signal to the parent when the child exits, so that the parent knows that the child has exited and it can extract the status of the child. Now, one more interesting thing that the clone system call provides us is the ability to unshare namespaces in Linux. So let's say we want the child process to be created in a completely separate IPC namespace, or separate network namespace, or a separate mount or user namespace. We can use the corresponding flags to do so. With this, we can use namespace isolation when creating a process, right? And this powerful feature provided by clone that allows processes to be created in completely different namespace in namespaces different than that of the parent is something which is used by the containerization technologies that we use nowadays. So that's another very powerful feature which is provided by clone system call is namespace level isolation. Not only namespace, but we can create processes in its own C group as well, which is pretty awesome. These are the advantages that clone system call brings to the table. Now again, since it's a system call, now the GNU C library or the glibc also provides us a library call which wraps around the clone system call. So let's see how we can create process using the clone library call. Okay, so now let's implement the same program that we wrote using the fork library call using the clone library call. That is, we will write a program where we will use clone to create a process which will print its PID, right? So let's see how we can achieve the same thing using the clone glibc library call. So I'll start by creating a new file called C source called pclone.c, and let's start with defining the necessary. So when using the clone library call, we need to define this macro called GNU source, and then we will proceed with the necessary header files. Let's create the function declaration for our function declaration for the function that will be called by a child process. Let's define the function now. Let's do the same thing, or let's simply copy this from our fork program code. Okay, now let's start with our main function. With clone, we need to specify the stack size and we need to allocate our stack memory before we call the clone call in the parent space. So in the parent space, so use a let's use a stack memory size of 65536, and let's allocate the stack memory of the same size. Let's do a tiny error check. Let's invoke our clone call. Just like the fork library call, the return value of a successful clone library call is also the PID of the child process that gets created. So let's store the PID of our child inside the same variable name that we used here, that is child PID, is child PID, right? And now we call our clone library call. Now one of the major differences between the fork library call and the clone library call is with fork we don't specify the function that the child process is supposed to run. How fork works is we call the fork library call and the program then gets cloned between the child and process. Like whatever line comes after the fork call, it gets executed in child as well as in the parent, and it's the programmer's responsibility to figure out when the program is running in the child and when it is running in the parent process. But with clone you can explicitly specify the function that you want to run in the child process, and the child process will start with running that function. So when you are calling clone, the first thing you need to specify is the function which the child is supposed to run, which in this case is child func. Then we need to specify the stack, and we need to remember that in Linux the stack grows from top to down. So we will need to provide the highest memory value or the highest memory address for our stack memory space. So for that we can simply pass stack plus stack size, and then the only, since we are replicating fork in this case, the only flag we will be sending is sick child. The last value is for argument that we want to pass to the child process. We don't want to pass any argument here. If we would have passed any argument here, we could have got it here, right? Uh, we could have got it, we could have got the argument here, but and then we could have used it inside our function, inside our child, but we don't want it as of now, so we'll simply pass 0. And and if child PID is -1, then we can say we can say that clone has errored out, and we can exit. Finally we can simply, oh, one more thing that we need to do is to keep things pretty much same. We'll we will have the same print statements. In this case there is no point of checking ourselves whether it is in parent or whether it is in child, so we will leave this line. We will simply try to print the return value of clone, right? And we will say that this is clone return value, and if everything goes right, this value and the value we are printing here and this value should be the same value, right? And finally we will wait for the child to extract its status. We will have we will need to define this variable child status, and what else did we do? Yeah, we finally will print the status of the exit status of the child. Okay, so that's pretty much it. We have a function which is executed by the child and it prints its PID. We malloc the stack space. We print the PID of the main program, which also happens to be the parent. We also print the return value of the clone in parent, and we also wait for the child to terminate, and we print the exit status of the child. That's it. So now let's compile and try to execute this program. gcc-g -p clone.c-o pclone. Okay, so it seems, let's change this to pproc, and I believe we also need to include syswait. Change this as well. Yes. Okay. Okay, so this is coming from the main program, and it's printing its PID, which is 19844, which is coming from this line. Then we have the clone return value, and the clone return value is which is from line number 32, which is 19845. And finally we have the print statement in the child, and here as well we are getting the child processor's PID, which is again 19845. So since the code ran as expected, the return value of the clone, which should be the PID of the child process, and the PID of the child process, which we are printing from inside the child process, both happens to be 19845, and hence we know the clone call executed as expected, right? So that's how you can use the clone library call to create processes as well in Linux using C. These are two of the most popular or the most used methods for creating processes in C. We also have the vfork library call, which uses the sys vfork, I believe. But again, that's not something which we will be checking out in this video. I wanted to share how one of the most go-to method of process creation, that is fork library call in C, uses clone under the hood, the clone system call, and how we can also achieve the same thing by using the clone library call from the GNU C library. So yes, that's it for this video, and I'll see you all the next time.